Hello, how's your day? Have you taken your breakfast? Do not skip breakfast, because it will give you the energy you needed to perform your work or job efficiently. It will also give you the strength to do your daily routine activities, like playing basketball, bicycling, wall climbing, among others. The food you ate will give you the amount of calories for you to perform these activities. Calorie is a unit of energy. Usually, the nutrition facts table, found at the back of the label of the food container, provides us a lot information, especially the calorie content per food serving. This food contains 80 calories per serving size of 16 grams. Food nutritionists have even calculated the amount of calories burned per hour for different activities. The values vary depending on the mass and intensity of the activity. From this table, we see that a 50-kilogram man, walking at a speed of 5 kilometers per hour, can burn 210 calories per hour of walking. Increasing the walking speed increases also the calories burned. An intense activity, like running at a speed of 16 kph in an hour, will consume 850 calories. So in order to maintain physically fit, you can do these following as exercises routine. You do not need expensive equipment to stay fit. But of course, indoor exercises is recommended during pandemic. We see that doing physical work can burn calories. Without energy, you cannot perform work. In physics, energy is defined as the capacity, or the ability to do work or to produce an effect. Energy and work are actually equivalent concepts. The release of energy does work, and doing work on something adds energy to it. With this property of equivalency, we can say that energy is also a scalar quantity, same as with work. The SI unit of energy is joule, pound-foot in English system, and calories in CGS system. Energy is a conservative quantity. The law of conservation of energy states that energy cannot be created nor destroyed but can be converted from one form to another. Here's a simple illustration. Imagine this boy gains 80 calories of energy from the food he taken. This stored energy can be used later to perform different activities. For instance, if the boy performs wall climbing, this 80 calories food energy is partly converted into 60 calories potential energy of the boy to lift himself. The remaining energy, 20 calories, will be stored in his body for later use. If all of these 80 calories have been consumed, the boy gets tired and he needs to eat again to replenish the energy lost by his body. Energy exists in different forms. Here, we will consider two forms of mechanical energy: kinetic energy and potential energy. The first form of energy that we are going to discuss is the kinetic energy. All bodies that move possess energy such as running car, a swinging pendulum, a supersonic speed bullet, and even smaller scale matter, like molecules and atoms. To illustrate this form of energy, consider a pendulum of mass m, tied on a nylon cord, and raised at certain height that when released, it swings and gains velocity v by gravity. At the bottom, there is a toy train resting on the table and properly placed so that it will be hit by the pendulum. The moment the pendulum hits the toy train, it will give the toy a force that causes the toy move along the table, thus performing work on it. This work is produced by the motion of the pendulum, therefore it has stored energy called kinetic energy. Kinetic energy, denoted by letter K, is a form of energy associated with the motion of an object. Mathematically, kinetic energy is expressed as 1/2 of mass m, times its square of the velocity. The SI unit of kinetic energy is joule, for as long as the unit of mass is in kilograms and its velocity is meter per second. We see from this equation that the kinetic energy of a body varies with mass and velocity. The more massive and faster the object moves, the more energetic it becomes. Now let us answer this problem. Problem number 5. A 1000 kilogram car is moving at a velocity of 30 meters per second. What is its kinetic energy? This problem looks simple. So we have given mass of the car, 1000 kilograms, and speed of 30 meters per second. So again, we are going to solve for the kinetic energy of the car. Since the car is in motion, therefore it possessed kinetic energy. Kinetic energy is 1/2 mv squared. Substituting the given information, 1/2 times 1000 kilograms, then times 30 meter per second, we square it. So the kinetic energy of the car is 450,000 joules or 450 kilojoules. And this is the amount of energy stored in the car due to its motion. If in case the driver decided to press the brake pedal, this is also the amount the work the friction on wheels must perform to stop the car. Now it's your turn. Exercise number 4. Which has more kinetic energy, a bullet of mass 0.02 kg, that travels at a speed of 300 meters per second, or a 800 kg car, moving at a 25 meters per second? Good luck. Work and kinetic energy are equivalent quantities. We see that kinetic energy can perform work and performing work on an object can change the kinetic energy of the body. This idea of equivalency of work and kinetic energy can be explained by a theorem called work energy theorem. It states that the work done by the net force on a particle equals the change in the body's kinetic energy. Now let us mathematically illustrate this theorem by applying the concepts we learned from Unit 1 and Unit 2. Imagine a box of mass m, moving at an initial velocity, v sub I, along a horizontal surface. An external force, exerted on the box, causes the box to accelerate at constant rate, a, that changes its velocity to a final value of v sub f, while undergoing a displacement of delta x. The time in which the net force acts is delta t. Now we are all set to explain how this expression was derived. First, we knew that the total work done by this external force, or by net force, is given by the expression, net force, summation of F, multiplied by the displacement, delta x. But we knew that, from Newton's second law, net force is equal to the mass of the body multiplied by its acceleration. So the total work done can be written as m(a) times delta x. Now we try to replace this acceleration in terms of velocities. From Unit 1, for a uniformly accelerated motion, acceleration is final velocity minus initial velocity divided by the time interval. With this, the total work done will be m multiplied by v sub f minus v sub I times delta x all over delta t. Or we can rearrange this as, we simply put delta t directly below delta x. This is to see that, from Unit 1, delta x divided by delta t is the average velocity. It follows that, again for a constant acceleration, average velocity is also the average value of the final and initial velocities. So the work equation becomes as m times the quantity, v sub f, minus v sub I multiplied by 1/2 of the quantity, v sub f plus v sub I. A little more algebra will simplify this equation as 1/2 of m times v sub f squared minus v sub I squared. If we distribute 1/2 of m to the square of the initial and final velocities, surprisingly, we see the expression 1/2 mv squared. And this is an expression for kinetic energy. Wow! Is that great? This 1/2 of m times v sub f squared is final kinetic energy, k sub f, while this 1/2 of m v sub I squared is the initial kinetic energy, k sub I. Lastly, the final kinetic energy minus the initial kinetic energy is the change in kinetic energy of the body. This expression shows that the total work done by the net force causes a change in kinetic energy of a body. and this expression is the work-energy theorem. In addition, this theorem also explains that when a body accelerates. Now let us apply work-energy theorem for this problem. Problem number 6. A 712 kg car is traveling horizontally at 5.6 meters per second, when a force acts on it for 8.4 seconds, changing its velocity to 10.2 meters per second. Letter A, what is the change in kinetic energy of the car? Letter B, how far did the car move while the force acted? Letter C, how large is the force? So again we analyze first the problem by giving some illustration. So this is the car. Its mass is 712 kilograms. It is traveling horizontally at an initial velocity of 5.6 meters per second. At this point, a net external force acts on the car. This force is actually the force exerted by the road on the car's wheel, as a consequence of the additional power exerted by the car's engine. And since there is a net force, therefore from Newton's second law, the car accelerates. This force acts for 8.4 seconds, increasing the velocity to a final value of 10.2 meters per second. Required quantities are letter A, the change in kinetic energy of the car, delta K. The distance or displacement of the car during this time, delta x, and the magnitude of the net force acting on the car. For letter A, the change in kinetic energy is final kinetic energy minus the initial kinetic energy. Or using the basic formula of kinetic energy, 1/2 mv squared. The equation becomes, 1/2 of mass times the quantity, v sub f squared, minus v sub I squared. Substituting the values. So the change in kinetic energy of the car is 25,874 joules. For letter B, we will again go back to Unit 1, assuming that the acceleration is constant. We have the equation, displacement, delta x equals 1/2 of the quantity v sub I, plus v sub f, multiplied by time interval, t. Substituting again the given information. So the car has traveled 66.36 meters, when the net force is acted on it. Any questions so far? Okay, let's continue. For letter C, we are going to determine the magnitude of the net force acting on the car. We see from work-energy theorem, that the total work done on the object is equal to the change in its kinetic energy. And this total work is actually the work done by the net force. This expression becomes, net force multiplied by the displacement, delta x, and this is equal to delta k. Then solving for the net force. Net force is equal to change in kinetic energy divided by displacement. That is 25,874 joules or Newton meter, divided by 66.36 meters. So the net force is 390 newtons. Any question, class? If you understood this problem, well, congratulations. You are able to see how Newton's second law of motion applies with energy concepts. With this, you can now solve unlimited number of similar problems that you may encounter in the future. Okay, my dear students. It's your turn. Let us see if you really learned. Try to answer this problem. Exercise number 5. A 10-gram bullet, perpendicularly penetrates a vertical wall 20 centimeters deep. If the average retarded force exerted on the bullet is 2000 newtons, what is the speed of the bullet as it hits the